Our exploration of the mathematical underpinnings for this course now brings us to strings and languages. And here you're probably going to see some stuff that you haven't seen before. In Automata, languages are where all the action is, and a language is just a set of strings. In turn, a string is a sequence of symbols that is drawn from an alphabet, and an alphabet is just a set of symbols. Now you can start to see why we've been focusing so much on sets and sequences. We frequently use the uppercase Greek letter sigma to represent a language's alphabet. An automaton is a machine that recognizes a language. We feed it a string, and it decides if that string is a member of the language that that machine is designed to recognize. A grammar, on the other hand, is a set of rules that generates a particular language. If we follow those rules, we can produce any string that is in the language, and we can only produce strings that are in the language. As already noted, strings are just sequences of symbols, nothing more. Consider the two strings x and y, shown here. We might be tempted to think that x is the value 42 and that y is some person's name, but that's not the case. X is not a number. It's just a string consisting of two symbols, a symbol that looks like a 4 followed by a symbol that looks like a 2. Similarly, the string y is just a sequence of 4 particular symbols in a particular order. While humans often ascribe meanings to strings, the machine that processes them doesn't care. They just process a sequence of symbols. So now let's get some terminology that we'll be using out of the way. If W was a string, then, like any sequence, the length of the string is indicated using the absolute value signs. The reverse of that string, which we'll use a fair bit, is indicated by using a superscript r. Like any sequence, we use epsilon to indicate the empty string, which is a string that has no symbols in it. For convenience and succinctness, strings are usually written as a single entity instead of listing them out as a sequence in parentheses. This is pretty intuitive and works fine most of the time, and whenever we want or need to be clear, we can always use the explicit sequence notation. Just like sets can be combined by unioning them, sequences can be combined by concatenating them, which merely means to tack one sequence, known as the suffix, onto the end of another, known as the prefix. This, like most operations, there is a symbol that is commonly used for this, and it is a small open circle placed where we would normally place the dot that is used to indicate multiplication. Like multiplication, that operator is often left out when there is little chance for misinterpretation. Unlike multiplication, as you can see, concatenation is not commutative. At times we want to indicate that a string is repeated a certain number of times, and drawing on the similarities between how we indicate repeated multiplication, we use an exponent to indicate repeated concatenation. But when working with strings that represent values, don't fall into the easy trap of thinking we are indicating repeated multiplication. We're not. We're only indicating repeated strings. Finally, we will be working with strings that are a combination of explicit characters from the alphabet and variables that represent other strings. It can be tricky being sure which characters are symbols and which characters are strings. Fortunately, the context usually provides the clues needed to make the distinction. In this example, because x and y were previously defined as strings, we conclude that that is what is meant here, while the other characters, which haven't been defined, are assumed to be symbols from the alphabet. A good rule, one that is implicitly violated in this example, is never use strings from the alphabet as variables to represent strings. The alphabet that x and y are drawn from implicitly includes all the digits and all the letters. So using x and y for variable names was ill-advised. A better choice might have been to use some Greek letters. We will see this in practice quite a bit. We will often need to work with pieces of strings, and so a subscript after a variable name usually indicates the symbol at a particular location within the string. The first symbol, by convention, having index 1. Occasionally we will work with a sequence of strings and use a variable name to refer to the entire sequence, in which case the subscript refers to the entire string at that position in the sequence. Again, context will usually make it pretty evident what is being discussed. Just as sets have subsets, sequences have subsequences. These are very common when dealing with strings, in which case we call them substrings. We say that a particular string, in this case S, is a substring of another string, here W, if W can be written as the concatenation of three strings with S in the middle. The prefix string X and the suffix string Y can be anything, including the empty string. If X and Y are both empty, then S and W are the same, which shows that every string is a subset of itself. If X is the empty string, then S is a prefix of W, while if Y is the empty string, then S is a suffix of W. The meaning of proper prefix and proper suffix should be pretty apparent at this point. So how do we define a language? Simple, just like we do any other set. We merely describe what strings are and are not in the language. Here is an example of a formal definition like we will see frequently. This is read as follows. The language L is the set consisting of all W such that W can be written as the concatenation of A, X, and B, where the alphabet is the set consisting of A, B, and C, and the string X is any string from the alphabet starred. The star operator, more properly known as the clean star, in honor of Stephen Clean, who first defined it, merely indicates a set of all possible strings that could be constructed from the set being starred. It indicates repeated concatenation 0 or more times. We will introduce this operation when we look at regular languages early in the course. As with sets in general, any description that clearly defines the set will suffice. Hence, we could define this set less formally as all strings that start with an A and end with a B, with 0 or more characters between them, all of which are from the set A, B, and C. Now, while languages are unordered sets, it's often useful to order the strings in them for other purposes. First, we assign an order to the symbols in the alphabet. If the alphabet are numeric digits or letters, the order is pretty obvious. For broader alphabets, a common ordering is to use an existing character code such as ASCII or Unicode, but we are free to assign whatever ordering meets our needs. Once the alphabet is ordered, we have two common ways to order the strings made from it. Lexicographical order is when we order the strings according to increasingly longer prefixes. This is the same way that a dictionary does it, and so this is often referred to as dictionary order. Shortlex, which is very useful for many of the things we're going to be doing, first orders the strings by increasing length, and then uses dictionary order within each group of strings having the same length. Now, you might be wondering why we are focusing so much on strings and languages that are sets of strings. It's because languages equal problems. All problems can be cast as a language. Certain strings represent a solution to the problem. A particular string is in the language associated with that problem if and only if it is one of these strings. A machine that recognizes a language recognizes whether a proposed solution represented by a string actually is a solution to the associated problem. Going the other way, a grammar that generates the language generates solutions to that problem. Now, crafting such a language for an arbitrary problem is in general very difficult, but we can craft languages for a variety of problems that have very profound impacts on our knowledge of computability and complexity. This means that the theory of computation is largely about understanding the limits on what types of languages that various types of machines can recognize, because that equates to the types of problems they can solve.